So let's start the last session of this course. You have any queries from the morning session? Okay, if you have, we can also take it later on. Okay, so the first session now is a very short session, which is based on this recent work. This paper is there on archive and is freely available for anyone. So the idea basically is, in the morning session we saw how we can actually implement ZAC OTFS, both the transmitter and the receiver, as using this discrete signal processing, right? So at the transmitter you take your discrete DT domain signal, you convert it to discrete time using this inverse DZT transform, and then after that you just convert it into a discrete time signal and you do your pulse shaping, right? And then at the receiver you do the match filtering here, and then you just do sampling and periodization. You get your discrete time periodic signal here, and then you just do a discrete ZAC transform, which gives you the DD domain, the discrete DD domain equivalent signal. Okay, it's very easy, and we already know what these transforms look like. For example, this is your DZT, and you can actually implement them using n-point FFTs. Okay, so it's possible to use FFT, the basic building blocks in OFDM, to actually kind of do this computation very fast. This paper, which I am going to discuss next, also has, in fact, the diagrams that I put in the slides in the morning are also in this paper. Okay, so this paper is kind of contains everything that we are discussing today, the first session also and the session now. So the starting point of this session is this slide, basically, where if you remember this IDZT, so it takes as input a quasi-periodic discrete delay Doppler signal, right, which has period m and n along delay and Doppler, and it gives you a discrete time signal at the output, which is periodic with period mn, right. Now this transform, instead of going directly from the discrete delay Doppler to discrete time, you can actually go from delay Doppler to discrete frequency, and then from discrete frequency to discrete time is very simple. It's your IDFT, right, inverse DFT, that all of you know. I mean, this is your inverse DFT. I mean, you have this xn, I mean, basically you have this, these are your this is your discrete frequency signal Si from I equal to 0 to mn minus 1, okay, and this is your discrete inverse discrete frequency transform. So you take Si and it gives you the discrete time signal, right. This all of you know, right, but I am going to fill in this missing block here. Okay. Now this transform is called the inverse discrete frequency ZAC transform, which takes your as input your discrete DD signal and gives you the discrete frequency representation of it, which is Si. Okay. So this is the transform. Si is given by IDFZT of XDD, and this is the mathematical equation. This is the and you can see from it, you can tell that okay, you can implement it using FFTs kind of operations, right. And so basically what this is your ith, on the ith frequency, what you have is basically you take your delay Doppler signal and you kind of you do a DFT kind of a thing. If you see here, this is like a DFT, it's along the delay, it's not exactly that, I mean, it's basically your k is going from 0 to m minus 1. So it's something along the delay domain. Okay. But this I is like a constant in this summation. It's only the summation goes from k to 0 to m minus 1. So it's over one period along the delay axis. You compute it like this, and you can mathematically show it's there in the paper. I mean, in fact, it's there in the book also in chapter 8. So it's very easy to show that if you take the cascade of this and this, you'll exactly get what IDZT is doing. Okay, it will exactly match. Okay, so I did not include the steps, but it's trivial. The reason why I am showing this is now what I am going to do is, if you remember in the first morning session, instead of these two blocks, what we had was just a single block here, which was IDZT, right. Now what I have done is I have split that into two blocks based on the previous slide, and the IDFT part of the previous slide, I am combining it with the rest of the pulse shaping. Okay. And what I realized is that this whole thing, starting from this SI all the way till XT is nothing but your CP OFDM modulator, but under the constraint that this particular filtering has to be sync, it cannot be anything else, and this window has to be the rectangular time window along with a cyclic prefix. I mean, otherwise your duration should be from 0 to capital T, but I am starting with minus TCP. So remember, at this point this signal ST over here is still infinite time, because see, if you go back to the transforms, this S of I, you can very easily see that it is also a periodic signal in the frequency domain. You replace this I with I plus Mn, this will not change, because if you do I plus Mn here, you will get a term which is k times Mn divided by Mn, which is 1, right. And if you put I plus Mn here, that also does not change. Why is that, Kevin? xdd of k comma I is the same as xdd of k comma I plus Mn, because this is a quasi periodic signal which is actually periodic. It is in fact periodic with Mn along both delay and Doppler. We saw in the first session in the morning today that this any DD domain signal which is quasi periodic with M and N is actually periodic with Mn along both delay and Doppler. So when you replace this I with I plus Mn, you have I plus Mn here, but that is the same as I, because this signal is exactly periodic with period Mn along both delay and Doppler, not even quasi periodic, exactly periodic.
The question,
yeah.
This equation, because typical it is similar to inverse DFT, right?
This one,
right.
Yeah, it is something like that.
Then the complex term usually is plus sign, right? Inverse Fourier transform is plus sign.
No, it is not inverse, it is something like Fourier transform actually, because you are going to the frequency domain. So from the delay, it's like from the delay domain you are going to the frequency. Yeah, so that's why you have minus. Inverse, because you are actually going. So my notation is that whenever you go from the delay Doppler domain to any other domain, I put an inverse there.
Okay.
Yeah, because for me the natural domain is the delay Doppler domain. That is where all the design and action is taking place, right? So if you go to any other domain, I just put inverse. That's fine. It's very easy to see that this S of I is periodic with Mn, right? And therefore this X of N will be also periodic with, if you do X of N plus Mn, then you will see that it will exactly be equal to X of N, right? Right, Kevin? Right. In fact, you know that the IDFT will always give you a periodic sequence, right? I mean DFT and DFT is defined for a periodic discrete time sequence, right? Right? I mean the basic definition, right? So this signal S of t, I mean because this X of N is infinite time, right? It's the output of the IDFT, right? So we saw that in the math right now. So and this will just make it into a continuous time signal followed by filtering with the sync, and windowing. So, when you window it, then that gets limited to this time interval, and because this signal is periodic, even when you filter it, it will still be periodic. Okay. And so, what will happen is, when you put this window, it will automatically, you will automatically get the cyclic prefix. From minus TCP to 0, it will be the cyclic prefix, because at this point, I mean this, at this x tilde t is basically a signal which is periodic with time period capital T. Why? Because x of n is periodic with a time period, in number of samples it is m into n, right. So, and the sampling duration between any two samples is 1 over b. So, after mn samples, how much time has passed? Mn multiplied with 1 over b, right. So, that is the period of this continuous time signal x tilde. So, this continuous time signal x tilde t is periodic in continuous time and has a period which is m into capital N times 1 over b. Is that correct, Kevin? Why do we multiply with 1 over b? Yeah, the sample time is 1 over b. B is the sampling rate, and the period of this x n is m into n samples. That is the period of x n, right? Capital M into capital N, that is the period of x n. Now, what is m into n divided by b? So, m into n divided by b, right. So, what I do is I multiply t on both sides, numerator and denominator, but this is equal to mn, right. So, this gets cut, you get t. So, that is why the time period of x tilde t, this continuous time signal, is a periodic signal of time period capital T, right. And when you, if you have a periodic signal and you filter it, you still get a periodic signal, right? That everybody knows, right. And the period is the same, capital T, and therefore, this S of t is an infinite periodic signal with period capital T. And when you multiply it with this time window, it will automatically happen that the part of this signal that you transmit from minus TCP to 0, from t equal to minus TCP to t equal to 0, it will just be a cyclic prefix automatically, because this signal was periodic, right, with capital T. So, that is why this whole thing with this carefully chosen time window and this carefully chosen filtering is nothing but the standard CP OFDM modulator which we are using in the phones right now. Okay, it's already, this part is already there in the standard, right. It's only this little part that we have to implement, but this is just very easily done in software using FFT libraries that are already available there, right. So, and of course, you do not need to, you need to calculate the output SI only for one period of frequencies, which is I equal to 0 to Mn minus 1, right, that is all. So, I think that this actually gives us a way by which we can implement ZAAC OTFS on existing platforms, okay, with very little change. It is just a little software change, and by doing that we can get all these benefits of ZAAC OTFS, basically robustness to Doppler and other things with just this small change. Isn't it beautiful? Yeah. Also, this IDFZT, this block, the complexity is very small because you use FFTs. So, it is roughly of order Mn times log of Mn. It is like doing a Mn point FFT, okay. The complexity is less than that. Interestingly, there is a very interesting thing that happens. If you choose capital, now capital M and capital N is in my control, right? It's always in my control. And basically I choose, capital M and capital N have to be positive integers, and their range is from 1 all the way till Bt. They cannot be less than 1, they cannot be more than Bt, right. A special case is when M is equal to 1 and capital N is equal to Bt. And that special case of Zach OTFS with this M and N and with these filters is nothing but your CP-OFDM modulator itself. And the reason is because when you go to when you choose capital M equal to 1, what happens to this block when you choose capital M equal to 1? It becomes an identity block, and you can see that here. You put capital M equal to 1, the summation goes away. This becomes 1 because this k can only be 0, right. When you put capital M equal to 1, the k can only be 0. We put k equal to 0, this becomes 1. So, what remains is only xdd 0 comma I, because when you choose capital M equal to 1, basically you are just collapsing your delay domain. The delay domain just becomes single element, that is it, it collapses, right. And basically Si is the same as xdd 0 comma I. So, Si is basically the same as xdd, right, it is just a copy, and therefore, your entire CP-OFDM is nothing, your Zach OTFS for this special case and with these filters is nothing but CP-OFDM itself. So, it is very easy in software, you just change this M and N parameter and you can change where you are. Okay. And not just that, this Zach OTFS is not just one modulation, it is a family of modulations, because you change your capital M, you get a different Zach OTFS. M equal to 1 is a special case, it becomes equal to CP-OFDM itself. You can change M 1, 2, 4, 8, right. For example, if B times T is 720, then you can choose M to be 1 and N to be 720, or M equal to 2 and 360, or 3 and 240, or 4 and 180, or 5 and so on and so forth, right. 144, 5 and 144, 6 and 120, 7 is not divisible, 8 and 90. Each one of them is a different Zach OTFS modulation, right. It's just a family of modulations.
So here the IDFT is the M times N point IDFT, right?
It's not exactly implemented like that. If you see this guy, this IDZT is actually implemented using FFTs. And this is, you can say that this IDFZT is simply IDZT followed by your DFT, which is the inverse of this thing, right. If you look at the cascade of IDZT followed by DFT, that is precisely this. And DFT you have to do this DFT, the inverse of this thing is an MN point DFT. The complexity of that is Mn times log Mn, and to do IDZT also you need Mn times log Mn. So, that is how you will typically implement this guy in ML. So, you have to do two, of course, for the Mn point DFT it is an Mn point DFT. IDZT over here, IDZT is this, right. So, you have to compute this for different small n from 0 to Mn minus 1, right. But what you should see here is that this xdd is quasi periodic. You have to do you have to write something down here, actually it is not so straightforward. X of n is this, but what is x of small n plus capital N? That looks similar but it will have, you can write, if you write it like a quasi-periodic thing, then it, it becomes easier to see how that FFT is coming in. Maybe we can discuss that after the class, after the lecture.
My another question is about the PAPR problem. It seems that you realize this off-game system, so probably you can have more degree of freedom to control the PAPR, right?
I think PAPR, even in OFDM, it's an issue, right?
Yes.
So it will remain to be like that here also. That is true. But we did measure the PAPR and it's almost the same like OFDM. There's not much difference. But there is a way of actually, I think the main problem with the PAPR is because of the pilot. Because you have a single strong pilot, right? And the pulse-on is nothing but a pulse train, right? So the energy of the signal is concentrated in the pulses. So the pulses will be very peaky, and that will lead to PAPR, right? So that's the problem with the pilot, because the pilot usually will be strong enough. And so we have a way of dealing with that. I will show it later, where you can actually spread the pilot over the entire bandwidth so that its PAPR comes down, and you also don't need any extra overhead of those pilot regions. And you can do something like a de-spreading and spreading at the transmitter, de-spreading of the pilot at the receiver. But I will come to that. That is what we have for this integrated sensing and communication. But I will quickly come to that, okay. But so this was, now coming to the receiver, right. So in the receiver we had this DZT, right. If you remember, at the end you had Yn, and then you had Yn, and then you have DZT, right. I am going to replace this DZT instead of going directly from the discrete delay Doppler all the way till the time. I will take this Yn, I will first go to my discrete frequency using a DFT, and then from there I can always go to my discrete delay Doppler. It is the opposite of what we did at the transmitter. And this transform is the inverse of the inverse discrete Fourier transform. So I call it the inverse of the discrete frequency Zark transform that we saw in the transmitter. So I call this as a discrete frequency Zark transform. There is a typo here, there should not be any I over here, okay. Please remove the I there. So what this discrete frequency Zark transform does is it takes the discrete frequency representation Yi and it gives you YDD, okay. And this is the equation for it. This is the equation. This also looks like an FFT type of operation, right. Also this, yeah, but you just need to.
That is 1D signal, but
Yeah.
the left hand side is 2D signal.
Yes, exactly, that is the difference, right. So now you need to calculate this only for k going from 0 to m minus 1 and L going from 0 to n minus 1, right. You only need to calculate for that range of values, okay, because otherwise this is quasi-periodic, right. So that is what I do. I go back to my DZT based implementation and I split. So the DZT was after Yn over here, right. I split it into DFT followed by DFZT. So you have Yn, you do a DFT and then this thing, right. And then the DFT part along with this match filtering, it turns out is nothing but your CP-OFDM demodulator, as long as this filter is the sync filter. But this one now is also a rectangular time window, but look at the duration of the time window, because you have to ignore the CP part. You have to ignore the cyclic prefix, so the duration is only from 0 to capital T, that is why. And then it does exactly what the CP-OFDM demodulator does. So what this means is that at your receiver you do not have to do anything, you just take this existing black box, I mean that is anyways, so these are your subcarriers, what you receive on the subcarriers. So, you take that and you just apply your DFZT. But when you apply this DFZT, you have to be careful enough to choose your M and N correctly. So, your M and N should be exactly what is there in the transmitter, the M and N that was used at the transmitter. It should be exactly the same M and N, right. And of course, this can also be computed in this much complexity. So, it is not much of a problem, this putting this block in runs very fast. The question although now is that this is not the complete Zach OTFS, because there are three reasons for it. Okay. The first reason is that your filters, both at the transmitter and the receiver, your windows, your time window and your filter is constrained because it's constrained by CPU OFDM basically, right. So, it has to be rectangular, this has to be sync. So, first of all you are constrained there. Secondly, the duration capital T can only be one of the possible durations of a OFDM symbol. So, for example, if you are using OFDM subcarrier spacing of 15, 30 or 60 kilohertz, then your capital T can either be 1 over 15 kilohertz, 1 over 30 kilohertz or 1 over 60 kilohertz. So, you are constrained in that, right. And what that implies is, because you remember that your Doppler period, which is nu p, okay, if you recollect, your total time is n times nu p, right. What this means is that sorry, this is wrong. Your T times nu p is n, right? Yeah, sorry. Okay. So, what this basically means is that your nu p is n divided by T. Okay. But 1 over T is your subcarrier spacing. So, finally what you get is your nu p is n times the subcarrier spacing, right? Right? So, what it means is that the nu p has to be an integer multiple of the subcarrier spacing, and therefore, tau p is the inverse of nu p. So, basically that is the constraint it puts on tau p and nu p. You cannot freely choose tau p and nu p to be anything, right. Unlike the case of Zach OTFS native implementation, there you are free to choose, it is unconstrained. You can choose any tau p, nu p, and you can choose these filters which suit you, right, which give you good performance. But here we get constrained because of the CPU OFDM, right, because we have to implement it over CPU OFDM. So, then it makes sense that once you put these constraints, does Zach OTFS still perform better than CPU OFDM, or its performance also gets constrained, right. So, we did some simulations which I will show you. So, I have 4 different scenarios here. Okay. So, scenario 1 and 2 is at 15 gigahertz. These are TDL-C channels as defined in this 3GPP technical report 38.901. Okay. So, TDL-C, TDL stands for tapped delay line models, and TDL-C is typically for a non-line of sight communication, when there is no line of sight between the transmitter and receiver. Okay. And we tried 2 different speeds. One is like a vehicular speed of 90 kilometers per hour. The other is more like a train speed, around 200 kilometers per hour. Okay. And for this one at this much gigahertz, you get a Doppler shift of 1.25 kilohertz. For the train speed, obviously it is much higher, it is around 3 kilohertz. In both cases, the delay profile is normal delay profile, urban macro. Okay. So, normal delay profile will basically mean a delay spread of around 2.5 microsecond or something like that. The third scenario is at lower frequency of 7 gigahertz, because I found that first of all 3GPP is considering this new band now for 6G, this band around 7 gigahertz or so. They are going to call it FR3 or something, and also in this band you do have aircraft to ground communication, and so for aircraft to ground communication, if you consider an aircraft flying at a very high speed of 1000 kilometers per hour, and then I am assuming a line of sight channel, okay. So you have a strong line of sight component. The delay spread will not be that much if you have a line of sight, so it's a short around 1 microsecond of delay spread, but the Doppler will be very high, around 6.5 kilohertz. This is the maximum Doppler shift. The Doppler spread will be double of this, because the Doppler can be negative and it can be positive also. So the total Doppler spread in this case will be somewhere around 13 kilohertz. And then I also try to demonstrate a case where there is no Doppler, okay. You have a non-line of sight channel in FR1, frequency range 1, 3.5 gigahertz, which is there in 5G, but I use a long delay profile. So this is when your delay spread is very large. That can happen in India, for example, or in Australia, where sometimes they have very large cells, or the inter-site distance is very large, for example, okay? Because some areas may not be very densely populated, and so the service provider will not find it economical to have very dense cells. So they will have like cells not being so dense, right, and in that case you might have these long delay channels also, right. So these are the 4 scenarios where I want to compare CPU OFDM performance with. One is the unconstrained ZAC, which is totally unconstrained. The other one is which is constrained by CPU OFDM when you implement it over CPU OFDM. So in all the cases I have to make sure that the packet size is the same, right. So I have a bandwidth of 720 kilohertz and a time duration of 1 millisecond, which means that the total dimensions I have is B times T, which is 720. So I have 720 dimensions with me to communicate. I compute the effective spectral efficiency, which I define like this. So I exactly do what happens in your 5G basically, right. In 5G you have your LDPC coding also, right. So the effective spectral efficiency is defined to be 1 minus the block error rate times the total number of information bits that you have transmitted, that is before your LDPC coding, because the output of the LDPC coding is the coded bits. So they contain redundancy. So but before the LDPC you have the information bits. So the number of those bits multiplied with 1 minus block error rate, because whenever you have block error rate, those bits are gone, right. And then so 1 minus BLER times number of information bits gives you the real number of information bits which you are able to on an average communicate with 0 error, and then that divided by the total time bandwidth product, which is 720, the number of dimensions. So that will basically give you how many bits per dimension basically. So what we do also is for each of these methods, whether it is CPU OFDM or CPU OFDM ZAC OTFS over CPU OFDM or the ZAC OTFS unconstrained, for all of them what I do is I also kind of optimize the spectral efficiency with respect to the modulation and coding MCS as it is specified in the standard. In the standard they have MCS 0 to 29, right. So when you have a good channel you will go to a higher MCS. So the MCS exactly defines what is the code rate of the LTPC code, and it also defines the modulation QAM order. The higher you go in the MCS, the code rate is higher and the QAM size is also higher, right. So I increase the MCS to the point that my block error rate average does not exceed 0.1. So my target block error rate is 0.1, okay. And so that is like an optimization for the spectral efficiency. For CP-OFDM, for 1 millisecond I will have 14 OFDM symbols. I mean, it is not always 1 second, 1 millisecond. For CP-OFDM, I just need to have one subframe of 14 basically, that is the unit. If you are using 15 kilohertz spacing, then it will be exactly 1 millisecond. But if you are using 30 kilohertz spacing, then what will happen is the duration will become half millisecond, but then I will double the number of the bandwidth will get doubled, so that the number of dimensions is still the same, right, 720. So, in the OFDM terminology, it will be 14 symbols and 4 PRBs, which is 48 subcarriers. That is for CP-OFDM. Okay. And of course, for CP-OFDM, we try out different values of subcarrier spacing, because to see which is the best in terms of spectral efficiency, and we also optimize with respect to the different, there are so many different pilot arrangements within a subframe. So, we run all of them exhaustively and see which one gives us the highest spectral efficiency. Okay. So, that the reason for that is nobody should say that we gave CP-OFDM an unfair chance, right. We are giving it the full chance as it is there in the standard. Okay. In the case of ZAAC OTFS, my frame is something like what we have already seen earlier with the pilot region, and of course, for the pilot region, this width along the delay. Now, the pilot region is basically a strip along the Doppler, because in all these scenarios, what is happening is, if you see, the Doppler is changing, right, but the delay is always not changing much. Okay. So, what we are doing is we put this pilot region along the Doppler as a strip. The width of this pilot region along the delay will be roughly equal to tau max is the maximum delay spread, and you divide by the delay resolution, which is 1 over b. So, b times tau max, those are the number of delay taps, you can say. That is roughly the width of this. On this side, because the delay is never negative, right. So, the information symbols on this side will not create too much interference for you, for the pilot, right. So, just one, so this width is only 1, it is just one delay tap, that is enough to stop this and this from interfering. Okay. But on this side, you will have to put width, a guard region which is of width equal to b times tau max, because this data, because delays are positive valued always, this data can actually come here in the yellow region, and it can disturb your estimation. So, you need to have some buffer zone here where it is empty, you are not sending any data, right. So, that is why you get b into tau max here, another b into tau max here, it becomes 2 into b tau max. Okay. So, 2 times b tau max, of course, plus 3, because we have 1 here and something here also, you need some extra margin, times capital N, because capital N is this width along the Doppler, right. If I look at this total region, the blue and the yellow combined, these are the number of dimensions or the number of delay Doppler taps where I am not sending any information at all. So, this is basically your overhead, right, for the pilot, right. So, if I divide that by m into n, that gives me the fractional pilot overhead. M into n is the total number of taps that I have, and that is basically this. So, obviously, the first condition is that the fraction cannot be more than 1. So, m has to be greater than this, okay, m has to be greater than this thing, right. That is the very first condition. So, that gives you a lower bound on the value of capital M that you have to choose. You cannot choose capital M to be arbitrary. And for capital N, I do not want to have any aliasing along the Doppler domain, right, because remember there is another pilot over here. If you add n to it, you will get another red dot here, right, and the response of that will be another pink ellipse over here. I do not want that pink ellipse and this pink ellipse to overlap. So, therefore, if you remember nu p, we always choose to be greater than 2 times nu max. If nu max is just the one-sided maximum Doppler shift. The total spread will be 2 times nu max. From here to here it is nu max, here to here it is minus nu max. So, the total is 2 times nu max. So, this nu p should be greater than 2 times nu max, and then if you multiply it with t on both sides, you get this equation, and n is equal to t times nu p. So, you get a lower bound on n also. So, you have to choose m and n such that this gets satisfied. And then of course, there is also this constraint that the product m into n is also constant, right. M into n is equal to Bt. So, you cannot choose a very large n, because if you choose your n to be very large, then your m will become small, because m into n is constant 720, and if m becomes very small, now this part is not in my control, because tau max is decided by the channel, B is already set to 720 kilohertz. So, this numerator is more or less fixed. If I choose my capital N, which is this weight, to be very large, my capital M will become small, and my pilot fraction overhead will increase, right. So, all these considerations have to be taken into account. And it turns out that when we actually did the simulations, okay, what we saw was, for Zach OTFS, when implemented over OFDM, the best spectral efficiency was almost always achieved when my capital N is equal to 1, which means this capital M is equal to B times T, which is the largest possible value of this capital M, because it gives you the lowest possible overhead in terms of the pilot. Okay. So, that is why you see for Zach OTFS over CPU OFDM, for all the scenarios 1, 2 and 3, n equal to 1 was the best. Okay. And for the last scenario 4, what we saw was the best case was when capital M is equal to 1, because there is no Doppler in that case. If you remember scenario 4, there is no Doppler, but M equal to 1 is same as OFDM. So, that is why there is no point in running Zach OTFS over OFDM, right. I mean, if OFDM is already good for the 0 Doppler case, there is no point in running that Zach OTFS over OFDM, right. As I said, the 1 over T, that is the I mean, you can either use 15 or 30 or 60, right. So, for scenario 1 we used 15 kilohertz, and that corresponds to these values of M and N. Pilot overhead is this much. In case of Zach OTFS, we saw that your pilot and data must have the same power for the estimation to be good, otherwise the estimation will be bad. Okay. Okay. And then of course, I mean these are the scenarios, all the 4 scenarios. The unconstrained Zach OTFS is also interesting, right. So, we run the scenarios, but in this case I can choose any value of my so, what I do is I choose of course, capital T is 1 millisecond, that is the total time, right. When you do Zach OTFS over CPU OFDM, you actually send 14 different Zach OTFS frames, because each transmission cannot be more than the length of a OFDM symbol, right. But when you are unconstrained, you can just send one transmission which is 1 millisecond long, right, and that is what we do. And therefore, your 1 over T is 1 kilohertz, right, in case of Zach OTFS. But we are free to choose the nu p. In the first and second scenarios, the Doppler is not very high. I think the highest was in second, it was around 3 kilohertz, which means the Doppler spread is around 6 kilohertz. So, as long as I choose my nu p to be more than 6 kilohertz, I am fine. Okay. So, we choose the nu p for both the scenarios to be 15, that is enough, because the largest Doppler spread you can get is 6 kilohertz only, and 15 is more than 6, right, and that corresponds to this M and N. If I use a higher value of nu p, I run into the problem that my M will be higher, right, because M is simply equal to B times nu p. So, M is what? It is B times tau p, sorry, B times tau p, yeah. So, this B divided by nu p is my M, 720 divided by 15 is 48. So, if I choose a higher value of nu p, the problem is that my M will reduce. For example, in this case, just see here, 720 and 24, my M reduces. And if my M reduces, then my pilot overhead will increase, right? So therefore, I should not unnecessarily increase nu P. I should only increase if I have to satisfy that crystallization condition. But in this case, 15 is good enough because it's much more than 6 kilohertz. But when we have scenario 3, where it's almost 6.5 kilohertz, which means the total Doppler spread is 13 kilohertz, and 13 is very close to 15. So you are at a risk of having strong Doppler domain aliasing. So that's why we had to increase the nu P and we went to 24. With 24 we got very good performance. Okay. The only problem was now your fractional overhead is slightly higher because your M is smaller, it's 30 now, right. Earlier it was 7 by 48, now it's 8 by 48. And the last scenario is when there is no Doppler. When there is no Doppler, there is no reason to choose a very high value of nu P. So we just choose the smallest possible value of nu P that we can choose. And the smallest value of nu P, if you see here, nu P has to be an integer multiple of 1 over T. 1 over T is 1 kilohertz. So the smallest multiple of 1 kilohertz is 1 kilohertz itself. So in this case where there is no Doppler, we choose 1 kilohertz, corresponds to n equal to 1 and m equal to 720. And there of course, I mean the pilot overhead is even smaller, very small. So these are the scenarios and these are the figures now, starting with scenario 1 where, so I increase on the x axis the signal to noise ratio. The signal, when I say signal to noise ratio, it means both the pilot and the data combined. Okay, so it's like the total power to noise ratio. This is the effective spectral efficiency. And what you see here is that I plotted all the different CPU FDM carrier spacings, 15, 30 and 60. 15 kilohertz is not very good, and the reason is because of ICI. Okay, so even though this is 1.25, the Doppler spread is still 2.5 kilohertz, and 2.5 kilohertz is only 6 times less than your subcarrier spacing of 15. So you will get some intercarrier interference because of that, and so that will degrade this performance, this one. So 30 is getting the best performance among in terms of OFDM performance, right, and with 60 kilohertz of spacing you get this. Okay. So 30 is the best because at 30 your ICI will not be there, even at 60 your ICI is not there. But the problem is with 60 you have a higher cyclic prefix overhead because the symbol duration is now shorter. Okay. So that's where the 60 is going to lose. Okay. So this is the best possible performance that you can get with CPU OFDM. Okay. And then on top of that I tried ZAC OTFS over CPU OFDM n equal to 1, which is here, the one with the square. Okay. And you can see that at 14 dB you get almost a 40% gain compared to this value. This value is somewhere around 0.65 and this is almost 1 or something like that. Okay. More than 0.9. So compared to this you get almost a 40% increase, even though I am constraining ZAC OTFS to be as per the CPU FDM numerology, still you get this 40% improvement, which is a lot. If you do your ZAC OTFS unconstrained, you still get a little bit extra improvement. It's not much. It's maybe 6 or 7%. Then the same story repeats when you go to a higher Doppler from 1.25 to 3. Now of course what happens is 15 kilohertz is totally out of the game. If I were to plot it, it will all show zeros because no matter what MCS I try, the block error rate is always higher than 0.1. I am not able to push bits if I use 15 kilohertz. So the best is 60 kilohertz of spacing because the Doppler now is very high. The Doppler spread is 13 kilohertz of Doppler. Even 30 kilohertz of spacing is not enough. So I go to 60 and 60 I get this performance, which is not very good, and it's much better than that is this performance of ZAC OTFS over CPU FDM. Now what you get with ZAC OTFS over CPU FDM is almost 1.5 times more. Isn't that amazing, right? Beyond what this is getting. I mean this I mean here the value is I think only 0.4 or something like that. What you achieve with ZAAC OTFS over OFDM is almost 2.5 times that. It's a major improvement, right? Again, ZAAC OTFS unconstrained gives you a little extra benefit beyond that. But when the Doppler really becomes very high, then your ZAAC OTFS over OFDM, okay, I mean, it still stays the same, okay, as the previous graph, but this unconstrained ZAAC, it gets much better performance than ZAAC OTFS over OFDM. So for high Dopplers, it makes a lot of sense to go to unconstrained ZAAC, okay. But even in these scenarios, your ZAAC OTFS over OFDM still gets a very comprehensive, improvement in the spectral efficiency compared to this CP OFDM, right. And then there was this last scenario number 4, okay, where what I said was there is no mobility at all. There is a very long delay channel, okay, and the delay is almost like almost 10 microseconds, okay. And when I simulated OFDM, CP OFDM, the performance with 15 kilohertz, I mean you would think that it should be good, but it was really bad. It was really bad. Why, Kevin, why do you think it was bad? CP OFDM performance when the delay spread is 10 microseconds? Because the cyclic prefix is only 4.7 microsecond. So the consecutive symbols were kind of interfering with each other very strongly, inter-symbol interference, and because of that it becomes bad. And the same problem will happen with ZAAC OTFS over, when you implement it over CP OFDM, there also you have CP. So you will have problems there also. But when you do the unconstrained ZAAC, it's not a problem, because in the unconstrained ZAAC also you put a CP, but you can put a CP of 10 microseconds, right, let us say. But the 10 microsecond is not an overhead at all, because you have the total packet duration is 1 millisecond in unconstrained ZAAC, and the guard time between different unconstrained ZAAC packets is only 10 microsecond, which is nothing compared to 1 millisecond, right. It's maybe 1%, that's it. So that's why there's not much of an overhead, and obviously with the unconstrained ZAAC the symbols don't interfere, and so you get very good performance. So this is an example where people typically talk about, when they talk about OTFS, they usually say that it's basically for the mobility channels, but it's not really that. I mean, look at this example here, right. It can also be used for high delay spread channels where the delay spread is very high. It's applicable there also. One more problem that you run into, and one more reason why the performance here is not good with 60 kilohertz, is when you have, imagine you have a delay spread of 10 microseconds. Your coherence bandwidth is small, it's only 100 kilohertz, maybe less than that. Coherence bandwidth is inversely proportional to the delay spread, right. If you have a large delay spread, then in the frequency your channel changes much faster. Now let us say your coherence bandwidth is less than 100 kilohertz. So what that means is that every other subcarrier has to be a pilot, because you are at 60 kilohertz of, well, even though this is 15 kilohertz spacing, I mean in 100 kilohertz you will do the phase of the channel will change by 2 pi radians, right. So if you consider 1/4 of that is pi by 2, which is still significant change in the phase of the channel, right. This is along the subcarriers. So 100 kilohertz is inverse of 10 microsecond, you divide that by 4, you get 25 kilohertz. So every 25 kilohertz your frequency domain channel is rotating by 90 degrees, right, which is a lot. And what that means is that every second carrier therefore has to be a pilot, and so you will get a big hit in terms of the pilot overhead along the frequency domain. So that is another problem there. Okay, this is another study that we had done in the past using a vehicular A channel model in ITU, but this is an old channel model. Okay. And we did the same kind of optimization, but this is not for ZAAC OTFS over OFDM. It is just the unconstrained ZAAC, okay, with respect to CPU OFDM. And what we did was we created many different kinds of channels with different values of nu max and tau max. So, nu max is the maximum Doppler shift, and so we tried these many different values of nu max, how many of them? 7 of them, and 5 different values of the delay spread. So, totally there are 35 boxes here, 35 different cases, and for each case we optimize the CPU OFDM over all subcarrier, pilot arrangements, MCS, everything, and we find the best throughput that CPU OFDM can get. And we also optimize the unconstrained ZAAC OTFS performance, okay, with respect to the delay Doppler period and also the filters. We were using a Gauss sync filter, I think that's giving the best performance. And we plot here in each box the ratio of the effective spectral efficiency achieved by unconstrained ZAAC OTFS divided by the effective spectral efficiency achieved by CPU OFDM. And as you can see in this lower quadrant, so this lower quadrant is basically small cells where you have low delay spread and you have very low mobility, right. So, there this ratio is very close to 1, okay, it is almost 1 actually, and that is expected. I mean, CPU OFDM is going to do good when you have low mobility, right. But when you go to the right side where you have higher mobility, you will see that the ratio is now much more than 1, right. In fact, in this extreme upper corner the numbers are really huge. Look at 2.39 or 2.61. Here it is infinity because for these scenarios CPU OFDM was not even able to get 0.1 block error rate. The total transmit power was constrained to 12 dB with respect to the noise power, okay. So, it is not very high SNR because that is typically what the systems in practice they experience. You will never, very rarely are you going to experience a 30 dB SNR, not so common, because majority of the people are always near the cell edge, okay, that is why. An interesting thing also, you get these numbers are very high, higher than 1 when your delay spread is high, okay. Of course, I mean people have to study. I mean, this is only the physical layer, right. The other problem is when you have 0.1 as your target, there are going to be retransmissions, right, because 0.1 is not that low, and the retransmission. So, somebody needs to also do this comparison with a higher layer where you have this HARQ and retransmissions and everything, and from that higher layer then we see what is the actual throughput. I am sure in CPU OFDM you will have lot of packet drops, I mean, and retransmissions which will further lower down your throughput. Whereas in case of OTFS, as long as it is in the crystalline regime, I showed you that it experiences no fading effect, and the actual received SNR is more or less constant. Whereas in frequency domain, you know, even across the subcarriers you have up and down, right, you have fading. Somebody has to do a research in that direction to do this kind of a comparison from a higher layer where you have all this ARQ and other things going on, right. Also, what happens if this target rate is not 10 power minus 1 but 10 power minus 2? So, we have to also simulate that and see what happens. I believe these numbers will become even higher because OFDM may not be even able to achieve sometimes 10 power minus 2, right. This is what I was talking about, and that brings me to the last part of the course. I will quickly go over some of these are some applications, because I have been so far only talking about communication, right. How does ZAAC OTFS improve communication for these new scenarios in 6G, but in 6G we have these other things like integrated sensing and communication, right, and radar, right. So, how does ZAAC OTFS address that is what I am going to talk about. Starting with Professor's question about PAPR, right. One problem with using this kind of I call this as a point pilot, because it's localized, it's a pulse-on at a particular delay Doppler, right? The problem with this point pilot is, first of all, you need this much of guard region and pilot region, that's an overhead. And also the PAPR is high, because the total data power and the pilot power are equal. The data power is still spread over so many pulsons, but the pilot power has to be localized at a single pulson. And so the PAPR is going to be quite, that's an issue, right? I mean, this is how the pilot signal I have plotted in the time domain is going to look like. I've just plotted the magnitude, and you see it has these peaks. Of course, this time interval is equal to tau p. Tau p is the time between two different pulses, and these are the pulses. So you have peaky pulses because energy is concentrated there. In between, there's not much. So this kind of a signal will have high PAPR, right? This is your pulson, the magnitude of the pulson. It's not looking like a sine because I have taken the magnitude here of the complex number. Otherwise, if I just plot the real part, then you'll see that sine modulation with a sine also. So here is the idea. The idea was that instead of sending a point pilot like this, I mean, this is your point pilot, right? This is the pilot at Kp Lp. We have seen this equation before, right? What I will do is, I will take the point pilot and I will filter it. Now this filtering is happening in the discrete delay Doppler domain, okay? I will use this filter, okay, Ws, and when I do that, I get this pilot which is spread, and I have shown the heat map here, 0 to m and 0 to n. So what happens is, this single pilot was yellow because all the power was concentrated there, but when you spread this pilot like this, the pilot becomes spread over all the pulsons. The pilot becomes like a linear combination of all the mn pulsons, and then the energy of each pulson will come down as 1 over mn, right? And because that's why the plot now here becomes green in this case, right? M into n is somewhere around 1000, if you see. So the power will come down by 1000 times, right, for each pulson. So 1000 times less is like minus 30 dB, which is here. That's why you see the green color, okay. The good thing about that is, now if you plot the same, so this pilot I am calling it as a spread pilot, okay. If you plot the spread pilot, you see that it's no more peaky, it's less peaky compared to your point pilot. So the PAPR is going to decrease, okay, this way. So here you have the PAPR curve, okay. The probability that the PAPR exceeds the x-axis. So what you have in red is basically the spread pilot. So it never exceeds 5 dB PAPR. Whereas if you have a point pilot alone, there is no data, then the PAPR can be very high. But when you have a point pilot with data, then the PAPR is less than 10 dB, around 10 dB, which is what is that's something like the OFDM number, right? OFDM PAPR is somewhere around 10 to 12 dB, something like that. But when you spread it, it all comes all the way down to 5 dB. So that's why spreading is a good thing, right? Yeah, this one is just showing some of the lattices that we have been using so far. This lattice which you see as the blue dots is basically your information lattice, right? Where this is the resolution along delay, which is 1 over b. The Doppler resolution between any two points is 1 over capital T, right? Now these green dots, the green ones are basically your the distance from here to here is one delay period. So we call that as a period lattice, okay. So along the delay, the green points are separated by your tau p, basically tau p, okay, and along the Doppler they are separated by nu p, okay. And then you have the outermost grid, which is shown in red, and there of course along the time you are separated by capital T along bandwidth you are separated with capital B. So this is for the continuous delay Doppler. Okay, you can also find the corresponding for the discrete delay Doppler. There's a little bit of math here. It turns out that this twisted convolution with this filter WS, okay, can actually, because this signal is quasi-periodic, right. So it's just like when you have a discrete time signal, which is periodic, and you filter it with a discrete time filter, right, then the output is still a periodic signal, periodic discrete time signal, right. But this is linear convolution, right. But you can write the same thing as a circular convolution of the signal with the periodized version of the filter. You take the filter and you periodize with respect to the period, and then you can write the same thing as a circular convolution with the periodized filter with the same input. And the same result is true here also. This twisted convolution, you can write it as a periodic. So this is a form of twisted convolution where remember your k prime and L prime, right. If you go back to your twisted convolution formula, will usually go from minus infinity to plus infinity, but here they only go over mn, period of mn, from 0 to mn minus 1, mn minus 1. But the formula is the same basically, it's just that so even there, in case of discrete time, your circular convolution is only over one period, right, it is not the infinite. So here also you are only going over one period, your summation is only over one period along delay and one complete period along Doppler, which is mn and mn in both directions. Okay. And this WKL is basically that original filter being periodized. There is a double summation here. This is the periodization. So I call it the mn periodic extension of WS, that is my W. Okay. You take the initial filter WS and you periodize it along both Doppler and delay with a period of M times capital N. Okay. Because capital M times capital N is actually the period of your XDD, your delay Doppler signal along Doppler and along delay. It is the exact period, okay, capital M into capital N. So what this tells us is that if I have two filters, okay, so let us say WS1 and WS2, but if their periodic extension is the same, then they will give me the same effect. So for me they are the same object, they are the same filter if their periodic extension is the same. Just like in the case of discrete time filtering, if the periodic extension of a discrete time filter, if of two different filters is the same, then the convolution with that periodic signal will be the same result for both of them, right. So that is why, so that actually kind of, I think that makes the filter design as a finite optimization problem, because now your filter, this WKL, if you see here, it depends on WKL only for k going from 0 to mn minus 1, L going from 0 to mn minus 1. So the number of different coefficients here is m square into n square, finite, it is not infinite, right. So you need to just design although that m square into n square may be large, but it is still a finite problem, right. So that is the advantage with this thing. What we tried was, that is what I have said here, that discrete filters are mn by mn dimensional, m square n square. Response of two discrete filters having the same periodic expansion is the same. Okay. In this example, I start with this chirp filter. Okay. So this is the chirp filter, the slope is q here. Okay. It's just a specific design. Okay. And I do the filtering with the chirp filter, and this is what I do. My XDD has two parts. One is my data signal, these are the data pulsons, okay, and this one is my spread pilot, and I scale them. This is the energy of the pilot, this is the energy of the data, okay, and this is combined together, that is my signal. And now in the data part there is no guard region or anything, it is all. So, here I have m into n data symbols, all values of k 0 to m minus 1, L going from 0 to n minus 1, all mn values. So, it is like overlaying your pilot on top of the data, right. This way you save the overhead, okay. And the received signal will therefore be the twisted convolution of this thing with H effective, which will give you basically these two terms, because H effective will get convolved with the data part and with the pilot part, right. So, this is your received data signal, this is the received sensing, I call it the sensing signal, okay. So, all of this is from this paper. Now, before I go to how do I do sensing in the, now basically once you have received this signal, I need to somehow extract out H effective, isn't it? I need to do the estimation, right. How do I do that? I mean, that is the first question that will come to your mind. In the case of point pilot, the estimation was very easy, right, because you were somehow avoiding the data and interference by putting this guard region, right. So, you were exactly getting very clean response of the point pilot, but now everything is mixed, right. You are sending information data as well as pilot on the same pulsons. It is just that for the pilot I am doing a spreading with a chirp filter. For the data there is no spreading. So, how do I estimate H effective? Before we understand that, we want to go back to the discrete time domain, and let us understand how do we do channel sensing in the discrete time, okay, right. If we understand that, then we can just take that idea and use it here. Okay. Now, suppose in the discrete time I have a signal xn, which is a discrete time periodic pilot signal with period capital P. Now, what is going to be your received pilot? Just a linear, I have an LTI channel, okay. So, Hn is the impulse response of the LTI channel, linear convolution with xn. So, this is the received, this yn is basically your received pilot. Now, from this yn I want to find out what my h of n is, that is the job, right. Okay. So, what I do is I calculate the autocorrelation function of between the transmitted pilot and the received pilot. That is what you do, right. It is very common, right, doing the autocorrelation function, and I call this autocorrelation as a y comma x. Okay. So, the value of the autocorrelation at the nth lag is simply the correlation between y and x delayed by n samples, right. So, you take your x, remember always that now in the setting x and y are both periodic, right. So, you take x, you delay it, and then you correlate with y, and you try out all possible delays, because in reality what the channel would have done is the channel would have delayed your signal, right. So, you keep delaying your input pilot and you take correlations with the received pilot, and so for each of these delays you will get some values of the correlation, right, and if the value is strong, it means that there was some reflector at that delay tap. So, the strength of that correlation is directly proportional to, right. So, I will show you how. This is the autocorrelation, the periodic autocorrelation of the transmitted pilot, and this everybody knows, right. I mean, you take the correlation of x with itself. For example, what's the I mean, for example, if you use a Z of Q sequence, you would have heard about it, right. So, you have Z of Q sequences, they are periodic sequences, okay, but they have this very nice property that their autocorrelation is ideal. It is a periodic Dirac delta. So, this is the autocorrelation for your Z of Q sequence, and you have many other sequences also like that, but they use a Z of Q in the standards, okay, that is why I took the name. And it turns out that you can show that AYX, okay, which is this formula, is exactly equal to Hn linearly convolved with the autocorrelation. So, the cross correlation of the received and the transmitted pilot is equal to the this is linear convolution of Hn with the autocorrelation of the pilot, okay. This is a very simple result that you can show. Now, when I have a pilot like the z of q, I know that this axx is basically equal to this. So, I replace this with this and then I do a convolution, I get this thing. You see this? Capital P was the period. Okay. So, what I am getting is I am getting my Hn and in the autocorrelation, but then I am getting copies of it. Now, these copies, so that they do not alias, I do not want them to alias, right. These are different copies of Hn. Hn, when you put k equal to 0 in this summation, you get Hn. When you put k equal to 1, what do you get? H of n minus capital P, that is a different signal, right. That is Hn delayed by capital P, which was the periodicity of your pilot, and then H of n minus 2p. There is also H of n plus p, which is negative delay, right. But these, if I choose my, now this Hn is going to have some delay spread. I mean, it has to, H of n is not like a Dirac delta, right. It will have some spread along discrete time, right. And so, the same spread will be for all the copies will also have some spread, right. Now, between the two copies, the distance is capital P. If that, so if the capital P is more than the spread of this Hn, then I can estimate my Hn very cleanly, right, because then these copies are not overlapping with each other. So, I choose my, see these ideas are already there in discrete time, I am just bringing them here, that is all I am doing, right. So, you just choose the period P to be greater than the delay spread of the channel, and by doing that you can exactly get your H of n back by doing this autocorrelation. Okay. You see the point, Kevin? Yeah, you will have to derive this, it is not very difficult, but once you derive this, then it is very easy. I mean, you take this, you put it here, you get this thing, right. And I mean, once you see this, then you know that your period capital P should be greater than the delay spread of the channel Hn, isn't it? I mean, these are like some of all those copies, right. It is just like the aliasing that we were discussing yesterday in delay Doppler. This is aliasing in the discrete time domain, right. Now, I am going to take this thing, I am going to extend this to delay Doppler basically, and not just time domain. So, my problem there was how am I going to find my, from this received signal, basically this which has all this data and noise and also the spread pilot, you know, twisted convolved with the channel, how am I going to get back my H effective? So, you probably have to do some kind of an autocorrelation in the DD domain between this received signal and the pilot signal, the spread pilot signal that you have transmitted, right. So, that is what I will show now. Now, your XSDD, okay, this is, so let this be the spread pilot that you transmitted, which was WKL and then the circular twisted convolution with the point pilot, right. That was X spread, this is the spread pilot. Obviously, this spread pilot has a discrete time realization, right, of period Mn, right. I mean, if you start with this and you take the inverse discrete Zark transform, you will get the you will get the discrete time realization. We have already seen that, right. This is the received pilot, and let us say that this YDD has a discrete time realization, which is Yn, again related by dzt. And now, how do I take, now this is the generalized definition of kind of an autocorrelation between the transmitted discrete time signal Xs and the received signal Yn. Okay. Again, these are all, there is no delay Doppler here, these are all discrete time. Okay. But I want to somehow capture also the effect of Doppler. Okay. See what I am doing, it is very easy. This is something like a discrete time correlation between what you have received, and now you take your signal Xs of n, which is the transmitted pilot, right. If I delay my transmitted pilot xs of n, which is this guy, if I delay it by k taps, k discrete time taps, and I give it a Doppler shift of L taps. Remember, your Doppler shift by L taps actually means a Doppler shift of L divided by Mn, because that entire m into n, that's like a shift by 2 pi. It's periodic with 2 pi, right? Sorry, I mean all these signals are periodic with Mn. So 2 pi is Mn, and therefore, but 2 pi has Mn taps. So if you shift by L equal to 1, that's like shifting by 2 pi divided by Mn radians. If you shift by L taps, the radians it will shift is 2 pi into L by Mn in terms of the discrete frequency. Okay. So when you want to shift in Doppler by L taps, then you have to multiply your, you delay it by k, and then you see the L here, L by Mn. So L by Mn times n minus k. Okay. So this signal is basically the same as my transmitted spread pilot, delay and Doppler shifted by k and L taps. And now I will take the autocorrelation or the cross correlation between this delay Doppler shifted spread pilot and the received discrete time pilot, right? And this is your autocorrelation. Again, this is circular, which means that this n minus k should be interpreted as modulo Mn, right? Because all of this is circular. I call it periodic cross correlation. Okay, because all these sequences x, s, y of n, they are all periodic with period capital M into capital N. Okay, and this I am calling it as, it's actually your autocorrelation basic. I mean, it's basically a cross correlation, but there is a specific name given to it in the literature. People call it as the cross ambiguity function. They call it as the discrete cross ambiguity function between y and x of s evaluated at k comma L, k delay taps and L Doppler taps. Okay, that's what you got. And if you do a little bit of math, which I am not shown here, but it's there in your book. If you go to the chapter 8, and not just, no need to probably go into the book. I mean, even if you go and see this paper, which is on archive, you'll see a proof which actually shows that this cross ambiguity is actually equal to H effective twisted convolved with, this is the auto ambiguity function. If you replace this y with x of s itself, what you get is the auto ambiguity function of your transmitted pilot, right. So this is the auto ambiguity twisted convolved with H effective is going to, so this is the result. Okay, I mean this is proven, I mean this is proven in that paper. Okay, and isn't it similar to what we had for the discrete time? See, here it was, see this result, the correlation is the channel linearly convolved with the auto correlation. You exactly get the same thing, but for your doubly spread channel. In the doubly spread channel, the convolution becomes twisted convolution. Your domain becomes the delay Doppler domain. This is the channel in the delay Doppler domain, and your autocorrelation becomes this ambiguity function basically. Okay, that's the mapping, right? But otherwise, conceptually, it's the same thing. Okay, so now we want to see what this is. In that case, with Z of Q, it became a pulse train. It was a periodic discrete time kind of Dirac delta function, the autocorrelation with period capital P, right. Let us see what we get here. So with the chirp filter, that WKL that I had designed, what you will see is that this autocorrelation, this particular guy, becomes discrete in the sense that auto ambiguity is 1, basically it is non-zero only at these blue dot locations. For all other values of k comma L, it is actually 0, and these points actually form a lattice. They are actually a lattice, they are points of a lattice, So basically what happens is your auto ambiguity, use a Chur filter, your auto ambiguity function gets supported on a lattice. See, even for the Z of Q, the autocorrelation was on a lattice actually, and the lattice was just the linear single dimensional lattice with period capital P. So, the points were 0, capital P, 2P and 3P, like that. That is also a lattice, but it is obviously in the single dimensional a lattice has to be like that. That is the only possibility. In 2 dimensions you have different possibilities of the lattice, right, and the lattice actually also depends on your value of Q, that is the slope of the Chur filter. You change your Q, the lattice will change. And now, so basically your auto ambiguity is supported on the lattice, and when you do a twisted convolution with H effective, what will happen is this H effective will go and sit on top of each of those lattice points, right. So, in this example I have taken H effective to be like a square region, okay, where the horizontal spread is equal to the delay spread. So, it is going from K max to K min, and then you have L max and L min on the vertical along the Doppler. Okay. So, this is going to be how the heat map of your received pilot is going to look like, where the one which is placed on 0, this one is exactly equal to your H effective. So, you can, but then again here we need to choose a proper value of Q, where here it is 5. If you choose Q equal to 4, you see the problem what is happening here. The lattice is different. Now all these copies start to overlap, and if they overlap then you cannot estimate your H effective, right. So, you have to choose your Q appropriately, right. So, that is how you do this de-spreading, basically this you have to calculate the cross ambiguity. Okay. But I mean this figure which I showed you, there was no data there, so it was quite clean, but you will actually have data also, right. So, when you were doing your ambiguity, cross ambiguity between, I mean in the received signal you cannot separate data and your pilot, right, the data is there. So, you simply take a cross ambiguity between your received signal with the transmitted pilot. So, there you get this term, well this is the good term, right, this is the one which we just saw now, right. But then you also get this part which is because of the data, and this actually is like a cross ambiguity between, I mean this one is the auto ambiguity of the pilot, spread pilot, and this is the cross ambiguity between the spread pilot and the data part, the data pulsons. Interestingly, what happens is this cross ambiguity does not have any lattice structure, because the data is on, they are not spread, right, whereas the spread pilot was spread using a filter, right. It is just like what you do in CDMA. If you use different codes for different bit streams, if you use different code and the codes are orthogonal, then you can separate them out, right, by doing a in CDMA that is what is done, right. So, you can think of this something very much like that, right. Now, this is the auto ambiguity between the data and the spread pilot. As you can see, it looks almost like floor, noise floor. Okay. In fact, all of them, the energy of all of them is 1 over Mn. So, this interference looks like noise. Okay. When you do this de-spreading thing, when you do the cross ambiguity, it becomes like noise. So, that is a very good thing, because then what it means is I can actually first from the received signal I do a cross ambiguity with the transmitted pilot, and from that I can estimate my channel. Then what I do is once I have a good estimate of the channel, I can cancel the received pilot. Once you know the H effective, you know what is the pilot that you would have received. So, you estimate the received pilot and you cancel it from the received signal, and then you have a pure data only signal with some residual pilot will be there, right. On that you do your equalization. Okay. So, that is the basic idea. So, that is what I have shown here, that at the transmitter you have the spread and the point pulson, you add them, you transmit, you receive both of them together in one signal, you first do a channel sensing, which is that cross ambiguity, you get the estimate. From the estimate, you make an estimate of the pulse on of the spread pilot, and you subtract the spread pilot from the received, you get a very clean signal which is mostly data, and you do the data detection equalization, and that is your thing, right. And we did some simulations, again this is old simulations with the vehicular A channel bandwidth of 1 megahertz, M and N are given here. So, M and N should be relatively prime and odd, okay. That is one constraint, otherwise the spreading does not happen very nicely with the chirp filter. This is the delay Doppler profile, 2.5 microseconds of delay. There are 6 paths, okay. Pulse shaping is I am using this RRC, root raised cosine pulses, instead of sync. So, here what I am showing is, yeah, so do not worry about this C bar, let us focus only on S by C. So, this is basically, we also ran some experiments to understand the normalized mean square error of this estimation that we are doing, right, what I just described now, right. So, as you increase the pilot power, what happens to the estimation error, right, it is like that. So, if you look at in the presence of data, so C means, so this is sensing in the presence of communication data, right, and this is sensing in the absence of data. Obviously, when you do not have any data, you have a frame with only the spread pilot, the NMSE is very good, but the moment you put data, it is not so good, right, it becomes bad, right, unless, and of course, you have to use a higher, your pilot has to become stronger, maybe the pilot. So, this is the pilot to data ratio, how strong is the pilot compared to the data. So, if you have 5 dB of your pilot is 5 dB more than the data, then you get a good normalized mean square error of 10 power minus 2, which is good for all practical purposes. At high values of the pilot to data ratio, both of them are flooring and they have the same value, which means that now here there is some effect which is not data basically, because anyways when your pilot to data ratio is 40-45 dB, data is almost absent, I mean the effect of data is not there. The only effect that is happening here in this case is the aliasing. So, remember you will also have aliasing, right, when you spread the pilot you are spreading in all the boxes. So, they will alias, right, and when the pilot becomes strong, the aliasing becomes the dominant effect, and that is why you see the floor here, okay. But usually we will never go in this regime, you will be around 5 dB or so, because 10 power minus 2 is good enough. The block, now this is uncoded simulation with 4 QAM, okay. The bit error rate, if you have the full, your sensing is performed on the same frame with in the presence of data, and also when you do the equalization, you have the data, I mean you have the pilot, some residual pilot also, right. So, when you do that, you get this blue curve, okay, like, so when you increase PDR, pilot to data ratio, initially you come down, and you come down because your pilot is becoming better, more powerful, your estimates are better. But when you go further high, what happens is, if the pilot really becomes very strong, then it will create interference for the data, and so the data detection will suffer there. I mean here the data detection improved because the accuracy of the pilots improved, but the moment they are more than 10 dB pilots compared to data, it starts affecting your data, that is why it goes up. So, you see this characteristic U shape, okay. I mean even if you cancel the data, even if you cancel the pilot, there is always some residual that remains, right. So, that residual is what is responsible for the increase in the later part, that is why you have the U shape, okay. Again the blue curve here, if you see, is now this is versus nu max, very interesting. So, as you increase Doppler, what happens to your bit error rate, okay, and I am only going till 14 kilohertz because my nu p is 30 kilohertz. So, I can tolerate even 14 because 14 times 2 is 28, which is still less than 30. So, that is why you still see, okay, 10 somewhere around 10 power minus 2, okay, although it is high, but the good thing is that it is flat. I mean the performance of even with the spread is almost invariant of the nu max, as long as you are satisfying the crystallization condition. Okay. But now remember, there are two different crystallization conditions here actually now in this case. One is obviously the crystallization condition for data, right, which is the delay spread should be less than tau p and the Doppler spread should be less than nu p, right. That is the classical. But then you also have that as far as your estimation is concerned, you do not want these guys to overlap. So your channel delay and Doppler spread should also be crystalline with respect to this lattice. For the data also you have a lattice, right, but that lattice is a rectangular lattice, the period lattice, where the period is capital M along the delay, along the Doppler it is capital N. That is the lattice for the data part, but for the pilot this is the other lattice. So now you have two different crystallization conditions which you must satisfy, right, because if you do not satisfy the lattice crystallization, your H effective will be bad, your estimate will suffer, right. And this is the effective throughput, again calculated, I think this one is probably with the LDPC code. Okay. And what we saw was that, so this is in blue you have your spread pilot, okay, with q equal to 3, that is very good. If you make q equal to 36, the black, you see what happens is bad. Suddenly after 2 kilohertz becomes very bad, because that lattice corresponding to q equal to 36 is not crystalline the moment your Doppler becomes more than 2000, and so your estimate becomes bad and your performance suffers and your throughput comes down. Okay. But q equal to 3 is just good. Okay. The other was comparison with the point pulse-on. Okay. Well, if I take a point pulse-on with a Doppler strip like a guard region, okay, its performance is good because you have the guard region, so your estimation of the pilot is very accurate. But then you have a loss in terms of the overhead of the pilot, and that is why the throughput is less than the throughput with spread. With spread you are roughly like 10% better than the point basically, right. Now I told you about this, estimating and then cancelling the spread pilot and then doing data detection. This can be done in a turbo manner, right. So after you finish data detection, you get a good estimate of the data, and now you cancel the data because you know H effective, you know data also. You cancel the data now from the received signal, you get a pure received pilot, spread pilot, and with which again you do the cross ambiguity. You get a better accurate than the first iteration of the estimate, and you have a better cancellation of the pilot, and therefore a better detection of the data, right. And you can, so your bit errors can be reduced like this. Okay. And so we do it 4-5 times in this turbo manner. So this is with the one iteration it was very bad, around 10 power minus 2. If you do 3 iterations you come down significantly, 5 iterations little bit of further improvement, and then at 10 also there is some improvement. But see, with 10 iterations you are almost as good as perfect CSI. So this black is a special frame where there is no pilot, and you are assuming that I know H effective, and you are not sending any spread pilot, you are just doing data demodulation, that is all. So with that you get this kind of a performance in black, and with 10 iterations you are almost there, except if the Doppler starts, when it starts to become higher Doppler, that is where you have the problem, because the aliasing is going to come into play now. Okay. One practical problem, and I will discuss these research problems, I forgot to add it in the last slide, is that one constraint with this turbo thing is that it needs high signal to noise ratio, otherwise you have the propagation of the errors. And so somebody has to solve that problem, because of that problem we are only able to work at very high SNRs around 20 dB or more, whereas in practical systems you can even have 10 dB SNR. Users which are at the cell edge may have 5 or 6 dB SNR. So how do we enable spread pilot for them also is something that is still a point to be. So here, I mean, now it's a different topic, right? It's radar, right? How do you use ZAC OTFS for radar? I mean, assume a radar scene where there is only a single target, there is no reflections, okay. You transmit this waveform, you receive this waveform, right. So, the target will delay your transmitted signal and will give some Doppler, right. And so, the signal will bounce off from the target and you will get it back. So, the delay is actually the round trip delay, and the Doppler will also be actually twice of the speed of that target, right. Now, from this received signal you have to estimate your delay and this Doppler, right. So, if you do a basic first year math, people who are studying detection and estimation theory, it is a problem for them. And so, the maximum likelihood estimate of the delay and Doppler is given by this function. You just maximize the cross ambiguity. This is the continuous delay Doppler cross ambiguity between the received and the transmitted, and it is the same as the discrete. You basically take your your signal S of t, you delay it by tau and you give a Doppler shift, okay, and then you do a correlation with your received, and you do this for different values of delay and Doppler. You see the value of delay and Doppler which gives you the maximum correlation, that is it, that is the delay and Doppler of your target, right, in simple language, right. But we call this function as the cross ambiguity function, okay. So, and when you have multiple targets, you will get multiple peaks of this cross ambiguity. So, each peak is a different target, right. So, that is how the radar world basically works. Of course, this is math and this is there in the book actually, if you go and read that. So, all this radar is in chapter 10 of the, very nicely done, okay. All these basic things are there in chapter 10 of the textbook. It turns out that this cross ambiguity is actually given by the channel, the delay Doppler spreading function of the channel, again twisted convolved with the auto ambiguity of the transmitted radar signal plus some noise, okay. This is the auto ambiguity, okay. So, you again see twisted convolution, it is not leaving you, it will not leave you, because that is how doubly spread channels behave. They behave or they act through twisted convolution and not linear convolution, right. And when you read, you will see that this twisted convolution is coming very naturally, it comes out just from nowhere. So, this is your received cross ambiguity, this is the auto ambiguity of your signal, and then there is this result by Moyal which says that the total energy of this cross ambiguity function in the delay Doppler is constant, is simply equal to the square of the energy of the signal that you transmitted. So, this auto ambiguity is like a finite thing which you can maybe move around, but the total is fixed. You have to think of it like that. If I use, let us say I am using sinusoids, OFDM, okay. I want to use sinusoids for estimating the delay and Doppler of a target, right. Sinusoids are not very, they are okay as far as estimating the Doppler is concerned, because if there is a Doppler, then your frequency will shift to another frequency, which is good. But for estimating delay, they are not good, because if you take a sinusoid and you delay it, it still looks like the same sinusoid. How do you find the delay, right? It will be difficult for you to estimate the delay. And the other way of mathematically saying that is that this is the ambiguity, the auto ambiguity of the sinusoid is shown in red, and along the delay domain the ambiguity is very large. I mean the ambiguity is very high, right. So, I mean this is the auto ambiguity. Even if let us say there was a delay of, so let us say capital T is 1 millisecond, that is the duration of the sinusoid, and there is a delay of 2 microseconds. Then what will you receive? What is the cross ambiguity that you will receive? The auto ambiguity twisted convolved with a delay. I mean if you see this function here, this is your red, that red thing twisted convolved with the channel which will give you a delay of 1 microsecond. So, what are you going to receive? The plot of this will be simply this red thing shifted to the right by 1 microsecond. but this is 1 millisecond long and you are shifting it by 1 microsecond. Can you detect that? No, you cannot make that out, because you will also have noise, right? You cannot make it out. That is what I was trying to say. I mean, because the ambiguity is so much along the delay, it is not good for delay estimation. Of course, along the Doppler axis, the ambiguity is very narrow, this function is very narrow. So, if you have a Doppler, this will just shift upwards, this whole red thing will shift upwards, and you can measure it because the width along the Doppler is 1 over t. The width along delay is capital T of this auto ambiguity thing. So, as long as your Doppler is more than 1 over t, the Doppler shift of the target is more than 1 over t, you can detect it, because this will shift by more than 1 over t, it will look like a separate thing, right? They will not interfere, right? And the opposite is also true when you use a time domain pulse. A narrow time domain pulse is very good for delay estimation, right? But not for frequency, not for Doppler estimation, right? And that is captured here mathematically as, if you look at the auto ambiguity function of a time domain pulse, then if you see along the delay it is very narrow, it is 1 over b. But look what is happening along the Doppler, it is equal to b itself. So, if you have a Doppler shift, right, the cross ambiguity will be simply this thing twisted convolved with the Doppler shift, it will just shift it upwards by a very, imagine b equal to 1 megahertz and you have a Doppler of 1 kilohertz. This whole thing is 1 megahertz and you are shifting it only by 1 kilohertz, you can't estimate that shift, okay. That is the problem, and basically again the problem is because your ambiguity, total ambiguity is 1, it is constant. See, this 1 over t multiplied with capital T is 1, that is the total energy of this waveform, right. You need to somehow redistribute this total ambiguity somehow, so that you can simultaneously estimate Doppler and delay accurately, okay. There was a gentleman called P.M. Woodward, and this is a very nice book, 1953. And he talks about probability, and this, I think this is good for undergraduates to study if they want to really understand the basics, very nicely written in this book. And Woodward is talking about radar, and he does not know all this theory about Zach and all this, he does not know at that time, because Zach came up with the Zach transform in 1967 and this is 1953, right. But he has in this book this design where he is so these are very narrow Gaussian pulses, okay, and they are separated by tau p. Tau p means tau d, basically in his language he is using tau d, okay, and then he is also modulating it with another Gaussian, he is multiplying the whole thing with a Gaussian time window. So, this is in the time domain, okay. And when you see the auto ambiguity of this waveform that Woodward was proposing in his book, you see a very nice interesting thing. You see that it is not like concentrated along one direction, he is dividing that entire ambiguity of 1 into small at points which are on this grid. So, each of this is very narrow, and these points are separated by, I think 1 over tau d. So, if this is tau d, right, then sorry, it is along tau d. So, along the delay domain, the separation of these points, these are ambiguity mass points. The total ambiguity is the sum of all the masses of these points, the black ones. So, these ambiguity mass points are separated along delay by tau d, which is actually my tau p. Remember my pulson, my pulses are separated by tau p, right. So, that is exactly this thing, right, and along the Doppler they are separated by 1 over tau d, which is my nu p, right. So, accidentally Woodward had an ad hoc construction of something like a pulson, it was not exactly a pulson because this is a Gaussian, it is not a sinusoid. He is getting the same effect, you see that. He is able to move the total ambiguity onto a lattice, right, and the advantage of that is, now if I have a channel, so now this is the auto ambiguity, it goes through a channel, right. So, as long as the delay shift is less than tau d and the Doppler shift is less than 1 over tau d, you can exactly and accurately measure. You can exactly measure these values, because see what you will receive, the cross ambiguity of the receive is just going to be this thing twisted convolved with the channel, right. So, that will just shift this whole thing, right. But when you shift it, so you see this blue box, I know that I will always know what is the maximum delay and what is the maximum Doppler shift that I am trying to of my system, right. So, I will only look at what I receive. I mean, when I look at the cross ambiguity, I will only see the black dots that I receive within this blue window, and there will be only one dot if there is one target, because I mean each of these black will have their own blue boxes, but they will not overlap. They will not overlap. So, if I choose my tau d appropriately to be greater, tau d should be greater than the maximum delay spread, 1 over tau d should be greater than the maximum Doppler spread. So, these were similar ideas which he had of, and the pulson exactly does this. This is actually the cross ambiguity, the auto ambiguity of the pulson. It is very much similar, right. So basically what we got is that Zach OTFS is in fact a very good radar waveform also, right, and it is good for communication also, right. So, we should use it for integrated sensing and communication, right. Of course, here now I mean this pulse, the shape of this, where the ambiguity mass point is, will depend on the pulse shaping of that when we do that WTX at the transmitter. So, that is the shape that will come here in the auto ambiguity. So, that will decide the shape of this mass point, how it looks. So, there is a bit of math that can be done in designing the WTX in such a way that you get some desired shape for these mass points, because they will not be Dirac deltas when we are using a physical pulson, right. They will have some spread. It will be, I mean along the delay it will be roughly 1 over b or something like that, along Doppler 1 over capital T. That in fact is the resolution therefore, right. I mean the spread of these mass points along the delay, I mean I call them the ambiguity mass points, because they form like an ambiguity region, right. If your target delay and Doppler shift is within that ambiguity, you can't estimate it appropriately. So, that is going to be 1 over b along delay and 1 over t along the Doppler. So, that is basically the resolution of your radar, if your OTFS with the radar. This is just an example. Here I am using Gaussian, the WTX is a Gaussian pulse, okay, and I have 4 targets. So, I transmitted a pulson at 0 0, which is at this point, right. Because there were 4 targets, I will receive, now this is in that blue box, I am not looking outside the blue box, this is within the blue box. So, because there are 4 targets, I will receive 4 different pulsons after reflection from them, but when I plot them, when I take the cross ambiguity of the transmitted and the received, I will see these 4, and I can easily, if I look at the center point, that is going to tell me what is the, so for example for this guy the center point is somewhere at this location. So, that from that you can compute what is the velocity and what is the distance of that target, and the complexity is very small. I mean you just have to do, you can implement this in discrete using again the discrete Zach transform at the receiver, and therefore the complexity is only mn times log mn, right, that is the complexity. Here I have just compared with other methods that are there in literature like music. So, you have these methods like music which have very high resolution, but then they involve inversion of matrices. So, the complexity is going to be cubic in your dimensions. K is equal to Bt, K is basically your Bt. K is actually the number of targets here. Yeah. I mean the maximum number of targets that we can support with Zach OTFS is equal to m into n, because remember my grid is m delay bins and n Doppler bins. So, as long as I have targets in each of the bins, I can easily separate them out. So, the maximum number of targets that I can resolve in ZAAC OTFS is m into n, right, and that's also equal to the bandwidth, okay, time bandwidth product, sorry. So, I mean the resolution is not very good with ZAAC OTFS, it's not as good as your music, but it's simpler to implement because you don't have to do any matrix inversion. I mean, you just take the ZAAC transform and you see it. It's something like that, right? I mean, of course, you have to do this auto ambiguity thing, but the auto ambiguity can be done in discrete time, okay. In fact, we also saw that even if you don't do the auto ambiguity, if you just take the ZAAC, transform the received signal, you still will get something very similar to this thing, this picture, very similar to this picture. And the reason now I know the reason for that. You know, the reason for that is because if you look at this cross ambiguity is the channel twisted convolved with this thing, right, with the auto ambiguity. But the auto ambiguity of a pulse-on is supported on that same lattice, on that period lattice. And so what you get basically H effective, H tau, you know, on the period lattice. But that is exactly what I will get if I just send a pulse-on at 0, 0. I receive and I don't even do this cross ambiguity business. I just look at my received signal in the delay Doppler domain. I take a ZAAC transform, that's all. I'll still see the same thing, right. So that's why you don't need to do all this, you know, you can just take the ZAAC transform, you will still get a very good this thing. I'll quickly finish with this chirps thing, Professor Kelvin. So chirps are very popularly used for delay and Doppler in radar, right. The problem with a chirp is that a single chirp is not enough. If you look at the ambiguity function, the auto ambiguity function of a chirp is basically a line like this, because nu is equal to at. A chirp is this signal basically, right, e to the j pi a t square. Your frequency is increasing linearly, right, at a constant rate of a. So that becomes the slope. So your auto ambiguity will be supported everywhere on this straight line. And when you, so what will you receive? What's the cross ambiguity of the received chirp with the transmitted chirp? You will just have to do a twisted convolution of this with the delay with the h of that target. So this will just be translated in delay, and you just have to shift in delay and Doppler by an amount equal to the delay and Doppler of that target, right. That's the received cross ambiguity. But then the line has ambiguity all over. I mean, even if it shifts, how do you tell what's the delay and Doppler of the target, right? So with just one chirp, you cannot exactly tell what's the delay and Doppler of the target. You need at least two chirps. So one is this chirp with an up slope a, another one is with a negative slope a, which is this one. And so obviously now the delay Doppler point has to be on both the lines, because both of them correspond to the same target, right, and therefore the delay Doppler is nothing but the intersection of these two lines basically. So that's how you calculate for chirps. But now you had to send two chirps. The total time duration is limited, it's the same capital T. So you give t by 2 the first chirp, t by 2 to the second chirp. The problem with that is when you reduce the time, the Doppler resolution becomes bad. And so this line becomes thick, more broader along the Doppler, and therefore this region will become more wider where the intersection is taking place, and so your accuracy will get a hit that way. Even bad is multiple Dopplers, multiple targets. When you have multiple targets and you are sending an up chirp and a down chirp, suppose you have 4 targets, then at the receiver when you do the cross ambiguity, you will not get one line, you will get 4 lines, right, all of them with the same slope, but they are shifted by different amount because the targets have different delay and Doppler shift, right. And then you also get 4 lines in the downward slope, right, but then the number of intersection points is how many? 16, but there are only 4 targets. So the remaining 12 which I have shown in red are what we call as the ghost targets. They are not really targets, right, they are ghost targets. There are only 4 of them which are actually the true targets, 1, 2, 3 and 4, right. Now, how do you distinguish between them? You have to send another pair of up and down chirp, but with different, not A and minus A, maybe 3A, 2A and minus 2A, something like that. So, you get another 16 points, but in those 16 points, those 4 points there and in the first pair that you send will be the same. So, that is how you resolve. But now, each individual chirp is T by 4, because you have 2 up and down chirps, right, 4 chirps you are sending. So, the resolution really becomes horrible, right, and that is when we simulated, we saw that when you do your ZAC OTFS, your range estimation error is much better compared to your chirp. Your chirp is basically in red, it's very bad. I mean, with your ZAC OTFS, your estimation error, I mean, in this example, I have a bandwidth of 4 megahertz, a signal which has a bandwidth of, the radar signal is 4 megahertz bandwidth, time duration is 20 milliseconds. These are the accuracies that you can get. I mean, chirp is really bad, OTFS is still much better than that. Also for velocity, you will get a similar thing. Okay. And now I will conclude. Where is velocity? I think I only showed only range. Velocity also has a similar plot. I wanted to add this problem of spread pilot, I forgot. So, the spread pilot problem is, can you make the same thing work at lower SNR, all the turbo and the cancellation of the pilot and all that, can you make that work at lower SNR? Maybe you have to use some other chirp, instead of chirp filter, use some other filter maybe. One severe problem is this low complexity equalization, because you have to equalize y equal to hx plus n, h is mn by mn, mn is typically of the order of 1000. You can't do an inversion, right, it will be really complicated. I told about one technique of actually doing the equalization in the frequency domain. So, that does, because the effective channel in the frequency domain is banded, so the complexity is still not cubic in Mn, it will become square in Mn, but it is still square. Can something be done to bring it to almost linear in Mn? So, that is one problem. There are people who are now started to look at ZAC OTFS MIMO, but there the problem is then each antenna has to send a different pilot, right. So, imagine the amount of pilot overhead will increase linearly with the number of antennas. So, what do? You cannot use that point pilot approach, it has to be a spread pilot, but then spread pilot has a problem at lower SNR, right. Then we have this problem in ZAC OTFS based prediction. If you want to really do artificial intelligence, you want to use ZAC OTFS to do prediction of the channel in packets and frames which come, let us say, after 100 milliseconds. And then the last one, which I was already telling, that you need to do a network layer kind of a simulation comparison to really see the effective, what is the really throughput difference. Yeah.
So regarding the channel sensing part, okay, you mentioned that when you calculate the class and you function of the pilot pulsons, okay, you will actually see the interference from the data pulsons. Okay.
Yeah.
So, but really conventional OTFS systems, okay, the pilot will actually decide different subcategories, so they are actually a pattern of the
exactly.
So you will see will not encounter this kind of problems. So my question is, how come so that you will see this interference in this ZAC OTFS
over CPU FDM?
Yeah, that's right. And in this is the overhead, although the old channels are predictable, which means you just need to estimate one channel, but you actually need the higher signal power for the pilot pump, so that you can kind of minimize this interference. So this kind of the the overhead or kind of the disadvantage of this approach.
No, when we were comparing all the transmit power, the total power for OFDM and ZAC OTFS is always kept to be the same. So, if the pilot to data ratio is higher in OTFS compared to OFDM, then the data power will be smaller compared to that in OFDM, because the total power has to be the same in both. So, yeah, so if it is 12 dB, then it's basically the power of the pilot and the data combined is 12 dB more than the noise power. So that way it is a fair comparison. So in terms of power, the comparison is fair. Overheads, of course, with point pilots, when we use them, we do have an overhead, right, because of the guard region and other things. But then we do, I mean, if you look at the unconstrained ZAC OTFS, then it doesn't really require a cyclic prefix. So you save there, right, because you have 1 millisecond frame, cyclic prefix is very small, 4 or 5 microseconds, not even 1%. Whereas typically in OFDM you have a 7 to 8% cyclic prefix, right. So you save there, but of course the point pilot does have an overhead. The spread pilot is good because it doesn't have any pilot overhead, but the problem is that it doesn't work at low SNR. And because what happens is when you cancel the pilot from the received signal, there is always some residual pilot that remains. And so what will happen is when you have low SNR, this turbo effect does not really come into effect really, because there is a lot of noise. And so you cannot, even if you think you have removed the pilot, but there is still noise there, right, which will, and so your channel estimate in the next cycle will still get affected by the noise. I mean, noise at low SNR, noise dominates everything, right. So your that calculation of the channel is not really helping you that much, because I mean the channel, I mean, imagine that you have 5 or 6 dB or 10 dB SNR. Even if you remove the pilot, the noise is still there, right. So so the channel estimate will not improve one cycle after another. So, and also remember, when we do the turbo, we also cancel the data. Before the estimation in the next cycle, we also cancel the data. But if your SNR is low, you will do errors in data. Not all your bits will be received correctly, right. And those data errors, when you cancel them, they will double that's called error propagation, right. And so that's why this thing will not work at low SNR. So some alternative method has to be there of how to make this spread pilot thing work, right, or how do we design spread pilots which have low cross correlation with the data part, something like that. So something needs to be done in that direction. But maybe I did not get your question exactly. Was it this or?
Oh, I say that in the ODM system, okay, that because the pilot form that we
orthogonal.
That's why you did not see this kind of interference outcomes in the OTFS.
I mean, in the OTFS, I mean, when we do the point pilot, it's almost, you can say, orthogonal, because you have the pilot region, so there's not much interference. So for the point pilot, you can say that they are almost orthogonal, right? But then you have to suffer with the overhead. That's because the guard region and the pilot region have this overhead, right? But see, even in CP-OFDM, once you have Doppler, then the pilots will also start creating interference for data, right? See, I mean, it's all good and they are all orthogonal as long as there is no Doppler, right? The moment you start seeing Doppler, the story changes. They also will see interference. Even for me, 4 or 5 years back, I was primarily a communication engineer, not a radar. But I wrote that chapter after reading different books, and so if you read that 10th chapter, you will get a very good idea of these things. And that's why I presented it as the ambiguity function as the natural extension of autocorrelation, right? of correlation basically. I mean the radar, the basic idea is very simple, right? You transmit a signal, right? And now when you receive your reflection, that reflection has to be your same signal that you transmitted, but delay and Doppler shifted by some amount, the unknown amount, right? So a simple common sense is that you know what signal you transmitted, right? So you take your, in case of radar, the transmitter and the receiver is the same thing. I transmit and I receive also. So I know what signal I transmitted. So I take my transmit signal and I delay it by different amounts and different amounts of Doppler shifts. So I get different copies of my transmitted signal with different delay and Dopplers. Which one of these signals is having the largest correlation with the received signal? The one which has the largest correlation is most likely the delay and Doppler shift of the target, right? It's common sense, right? That is what is your cross ambiguity, right?
So I like to thank everyone still be here for the past 2 days. I think although we run a little bit over time today, but I think everyone should, maybe just like me, I feel I learned a lot from Professor Mohammed. So once again, I'd like to thank all the attendees for coming to this micro class. And the second thing is I really like to thank Professor Mohammed. Actually, we started to invite him since beginning of June, okay? And after two months of arrangement, finally he was able to come to Taiwan, okay? Right before he fly to Taiwan, there's a typhoon. Everybody know that, right? So we were in debate, should we cancel the micro class or should we continue the micro class? So, but thanks God, Professor Mohammed was able to come and deliver a very two informative courses, 2-day courses to all the audience. So, and I can feel his enthusiasm about education, about research, about teaching. So I really thank you. Oh, and also I like to thank all the attendees. Without you, there's no today's lecture. And yesterday I asked our Secretary Zhao Pei, there are 55 people showed up yesterday.
Wow, amazing.
In the presence of typhoon. Okay, so, so I also like to thank everyone for coming. So
thank you so much.
Yeah, so Professor Mohammed actually spent a lot of time traveling. It took him 9 hours on the plane, and then and
if you want, I can come again. Anywhere on this earth.
Okay. So once again, I would like to thank Professor Mohammed. So on behalf of our alliance and also the director of our alliance, Professor Lin Kuan Zhang, we'd like to present a certificate of appreciation to Professor Mohammed for his for delivering a microclass here in National Zhongxin University, and so let us so we can get the first-hand insight regarding ZEC OTFS.
Thank you so much. Thank you so much, Professor Kelvin. Thank you so much. Yeah. Thank you very much. Thank you so much, Professor Kelvin. Thank you so much time to ensure that I was able to come here and deliver this lecture. For me, it's a very big thing, okay, and I respect that from the bottom of my heart.
It's our honor.
No, it's an honor for me actually to come here, and I always like to teach, to study and do research, and I never get tired therefore, and that's why I like interacting with all students, and thanks also to all faculty who gave 2 days of their time trying to listen to this new waveform. I mean, it's a lot, means a lot of encouragement for me that probably I'm on the right path. Okay, and so I have to thank you all for that, especially in this typhoon. 55 out of 60 people, which means there are a lot of people who did really travel and who came one day before, and from faraway places in Taiwan just for this course, and that's a lot of, that in itself is a lot of respect for me. Okay, so if there is any confusion about anything, you can please feel free to write an email to me. My email address is with Professor Kelvin, and I'll definitely reply back to you. Even if you need any help with the MATLAB code, I can help you with that. I have students, I can, they can do an online meeting with you and they can help you. Okay, but I'll really encourage you to, because this is a very new field, so there's a lot of possibility of doing some very good work and doing a lot of innovations. I mean, even this thing of using this Zark OTFS over OFDM is just the physical layer, right? I mean, if this has to be implemented on top of the existing protocol stack, there is a lot of, because if you look at the standard, you have the physical downlink shared channels for data, you have the synchronization channels, you have the random access, all of so many things, right? Now, how will you port all of them with the physical layer being replaced by this new thing? So there's a lot of patents and innovation that can come in that area. And so, I mean, Taiwan is good in semiconductor, so, and also good in communications, right? So you have so many good communication companies here, including MediaTek. So there's no reason why they cannot take this waveform, implement it in hardware, in semiconductor, right, and demonstrate that it's really good compared to, I think you all can do that, right? So thank you so much again. Yeah.
So sorry, we know the handbook we give to everyone. I think there are maybe some materials missing, so we will get it from Professor Mohammed, and we will we will give to the secretary Zhao Pei, and she will notify everybody when the complete handbook is ready. Okay, so everyone can get the complete information. Okay, so once again, thank you everyone for coming, and we now officially declare the micro class is finished. Thank you for coming.
For next time.
For next time.
Thank you.